Hey everyone, welcome back for part 2 of 3 of chapter 6. We left off, we had talked about entropy and how it relates to the second law of thermodynamics. So at this point, we're moving on with the chapter. Let's talk a little bit about spontaneous processes. So what is a spontaneous process? A spontaneous process has nothing to do with something that happens fast or slow. Spontaneous processes can be fast, they can be slow, but what they mean, what they are processes that occur without energy input. They are processes that occur without energy input. And not only that, what you should know is not only that, but they occur, when they occur, they release energy. So you may want to add that to your notes here. You could say it, and in fact, they release energy. Okay, so spontaneous processes occur without energy input and they release energy. Now that could be very quick, that could happen in a fraction of a second, that could happen over time. Okay, so some processes are spontaneous and some aren't. So for example, let me give you the easiest example I could think of. This guy on the platform, he has a high level of potential energy. So him simply falling into the lake, that would be a spontaneous process because it didn't take any energy to happen. And in fact, it released energy. In fact, he hit the water with a lot of force. But to climb back up, you see she's climbing back up to the platform. So that would be an example of a non-spontaneous process, right? So a non-spontaneous process would be getting up onto the platform. The spontaneous process would be falling into the water. Do you see how that works? And we could apply that to reactions as well. So for example, if I take a sugar molecule and I break it down into carbon dioxide and water, that's going to be a spontaneous process. But taking carbon dioxide and water and making sugar out of it again, that would of course be a non-spontaneous process. So spontaneous processes, if you can't tell, spontaneous processes release energy. Non-spontaneous processes require energy. Okay, they require energy. Okay, it requires energy to climb back up onto the platform. It requires no energy to fall into the lake. Does that make sense? So now you know what a spontaneous reaction is. And because of that, scientists wanted to know what types of reactions are going to be spontaneous and what kinds of reactions are going to be non-spontaneous. All right. So to answer that, in comes a gentleman named Gibbs, and Gibbs terms this phrase free energy. Okay, free energy. Okay, a living system's free energy is energy that can do work when temperature and pressure are uniform, as in a living cell. So what Gibbs said was that based on this free energy concept, this energy that can do work concept, we could figure out if a reaction is going to be spontaneous or not based on whether or not it starts with a higher free energy or the reaction starts out with lower free energy, and the direction of that change in free energy. Okay, so the free energy, the units for free energy are G, after Gibbs himself. And what we're looking at is the change in free energy, the change in G. So let me show you again. What's free energy? Energy that can do work. Let me give you a couple examples before we jump into this. Look at this guy. This gentleman's on the platform, and you see he's on the platform. So in this case, he has a lot of potential energy. That would be an example of more free energy, higher G value, right? The guy on the platform has a higher G value. Now, when he falls into the lake, he's said to have lower or less free energy, a lower G value. So what was the change in G between being up on the platform and being into the water? What was the change in G as you went from up here down here? It was let me just insert this for you. Insert. Okay, so it was the change in G was a negative delta G. And for delta, let me find that symbol for you guys. I want the symbol delta. Insert symbol. And I want, do you guys see delta? It should be under my used. Sorry. I will find, here's delta, you guys. Check that out. Now you know how to add a delta to PowerPoint. Okay, so anyway, when the gentleman's on the platform, he has a high G value. Okay, let me write that in for you guys. This is a high. Whoa, I don't know what happened to that text box. Technical difficulties, right? But we're learning PowerPoint together. High G value. You see? Being up on the platform means you have more ability to do work, a high G value. But what about being in the lake? What about being in the lake? Once he's in the lake, he has a lower G value. You see, so what is the change in G? You've gone from a high G value to a lower G value. So your change in G, you know what this delta means? Delta, this triangle means change, right? So how did your G value change? Well, you went from a high G value to a relatively low G value. You have a negative change in G. Okay? And do you know what Gibbs would say? Gibbs would say any process where you start with a high G value, and you remember what G value means? Free energy. And you end up with a lower G value, a lower free energy value. Gibbs would argue that that means that you have a negative delta G, and you know what that means? Minus delta G means spontaneous. Spontaneous. Okay, spontaneous. All right, does that make sense? So any process with a negative delta G is a spontaneous process. Why? Because you started with a high G value, a high free energy value, and you ended with a lower free energy value. Now, what would happen if the guy climbed back up onto the platform from the lake? What would happen? Then, in that case, you're going from a lower G value to a higher G value. What would your change in G be if you do that? If you climb back up the ladder? Well, in that case, your delta G would be, hold on, your delta G would be a positive delta G. You know why? Because you're going from a low G value to a high G value. That would be a positive change in G. You're going from low to high. That's a positive change in G. When you go from high to low, that's a negative change in G. Do you see that? So you could apply this to anything. So look at this example over here to the right. Again, look at this example. You put some dye, some molecules of dye, into a pool of water, right? You know, like a drop of ink. Is that drop going to just stay a drop of ink, or is that drop going to diffuse into the water? It will diffuse. The drop of ink will diffuse. And guess what? You may not have known this, but diffusion itself is a spontaneous process. You know why? Because there's a negative delta G. Why? Because the drop is the drop of dye constitutes a high free energy, and the dye, once dispersed, constitutes a lower G value, and the change in G is a negative change in G, a negative delta G. All right. The same thing with this. You see this molecule over on the right here? This molecule is sugar. Okay, so you have sugar. Do you think sugar has more ability to do work while it's sugar or after it's been broken down into CO2 and water? Well, it has a higher free energy as sugar. That's why we eat the sugars, we eat the fats, because they have a lot of chemical energy, which is a type of potential energy. And then once you burn that and you exhale, you exhale CO2 and water, that has a lower G value. So it's a spontaneous process. It's a spontaneous process to break down the sugar. But what about making sugar again? What about going from CO2 and water back up? That would be a positive delta G. See, I hope you're getting the point here. When you go from a high free energy value, a high G value, to a low free energy value, a low free energy value, a low G value, that is a spontaneous process. You go from high to low, that's a spontaneous process. It's a negative delta G, a negative change in G. When you go from low free energy, low G value, to high, that's a positive delta G, and that requires work. So let me write that here. Look, positive delta G means requires energy, requires work, requires energy to happen. So for example, if you wanted to take carbon dioxide and water and make sugar out of it, guess what? You're not doing that for free. It's not energetically free. You're going to require energy, okay? But if you want to take sugar and break it down into CO2 and water, that's free. In fact, that releases energy, and that's how we get the energy to move around and do all the things we want to do, right? That's how we exist, okay? All right, so a spontaneous process releases energy. It has a negative delta G. A non-spontaneous process requires energy and has a positive delta G. Okay, what if your delta G is 0? What if delta G is 0? Okay, let's talk about that. You see here, I don't know if they talked about it here, but I'll tell you. If your delta G, let me get the little delta here. Okay. If your delta G is 0, that means you are at equilibrium. Okay, so delta G equals 0 means you're at equilibrium. That means there's no net work being done. If your delta G is positive, it's... Oh, did I write spontaneous here? Ooh, you guys, I hope you caught me. If you have a positive delta G, that means non-spontaneous. If you have a negative delta G, that means spontaneous. I hope you guys caught me. Look, positive delta G is non-spontaneous, requires energy. Negative delta G would be spontaneous, releases energy. Okay, again, you're not going to make sugar from CO2 and water for free. It's going to require energy because it's a non-spontaneous process with a positive delta G. So, for example, you and I, we burn sugars into we burn sugars into carbon dioxide and water, and we get a lot of ATP out of that. We can move around and do exercise and whatnot. Do you know there are creatures that can take CO2 and water and convert that back into sugars? Do you know what that creature is? Photosynthesizers. Have you heard of photosynthesis? I just made a video on it, and we're going to be talking about photosynthesis in Chapter 8 later in the semester. But plants are constantly taking CO2 and water and making sugar out of that. Okay, and that is not a free process. That is not a free. That is not a spontaneous process. It's a positive delta G. It is a non-spontaneous reaction. Okay, so Gibbs, that's what Gibbs was all about. Gibbs wanted to. He coined free energy, the units of which are G, and he said what? He said very simply, if you have a negative change in G, that means spontaneous. If you have a positive change in G, that's definitely non-spontaneous. And if your change in G is 0, then it's at equilibrium. No work is being done. And remember what happens when you have a spontaneous process? Spontaneous process releases energy. Does not require energy, right? Non-spontaneous process requires energy input. Okay, and equilibrium, no work is being done. Okay, so hopefully that's clear. Okay, so basically Gibbs was a champion in this field of thermodynamics and uh, how to determine whether a process is spontaneous, not spontaneous. Okay, and it all depends on this G value and the change in G, right? This free energy. So he went on further to say, okay, look at this. He went on to define the parameters that drive spontaneous or non-spontaneous reactions, and to do so, he derived this equation. Okay, look at this equation: delta G equals delta H minus T delta S. Okay, what does that mean? Remember, delta G means change in free energy. We already know what delta G means. Let's work with this. Let's work with this. Let's erase this part for now. Okay, look at this equation. Delta G equals delta H minus T delta S. All right. So what can we do with this? Hold on. Let me explain this equation. This equation is great. The reason this equation is great is because Gibbs used this equation, derived this equation to determine whether a reaction is going to be spontaneous or non-spontaneous or at equilibrium. Okay, and it's very simple and beautiful because it's only got 1, 2, 3 parameters: H, T, and S. And if you look at the math, it's not very difficult math, is it? It's basic arithmetic. You've got this number minus this number times this number, right? So this number times this number. Okay, that's a real simple math problem. You multiply T by delta S, you then take H and subtract it by that product. Okay, so again, what is this equation? This equation is Gibbs equation, and this equation allows you to determine whether a reaction is going to be spontaneous, non-spontaneous, or at equilibrium. So how does it work? So what can delta G be? Okay, what can delta G be? Let's show you. Okay. So remember, delta G. If you have a negative delta G, okay, what does that mean? Spontaneous, right? Releases energy and requires no energy. Okay, that we already know. That we already know. Okay, let's put that over here. All right. So what does whoops, I'm sorry. Let's copy that. What does positive delta G mean? Positive delta G. Positive delta G means non-spontaneous. It definitely does not release energy. It requires. Spontaneous and requires energy, right, to happen. Okay, so we know if this number is negative, that means that we have a spontaneous process that we're dealing with. If this number is positive, then we know that we have a non-spontaneous process we're dealing with. And remember, if this number is 0, we are dealing with a process that has reached equilibrium. Okay, so what about H? What's H? Okay, look here. H is change in energy, total energy, or enthalpy, okay? H means enthalpy. H is enthalpy. Don't mistake that with entropy. It's enthalpy, okay? H, enthalpy. So, this is really confusing, isn't it? Enthalpy, or H, is the change in total energy. You might be wondering, well, how in the world is total energy different than free energy? Remember, free energy is the energy that can do work, okay? That's a little bit different than the change in total energy, okay? And I'll explain how. The simplest way to think about this, and probably as in-depth as we need to go, is you can think of it as if a reaction is losing total energy, it's giving off heat. If it is gaining total energy, it is absorbing heat. So I know that sounds confusing, but let's talk about it real quick. Look, Let me tell you. So again, if a equation is losing total energy, that means it has a negative change in total energy. It's losing total energy. It is giving off heat. All right, giving off heat. And if something is giving off heat, how does it feel? Like if I touch this can, and it's giving off heat, how does it feel when I touch that can? It feels hot, right? It feels hot or warm. Okay, so if you have a reaction going on and it's feeling hot, okay, it feels hot, then it's a reaction where you have a negative delta H. You have a negative change in enthalpy, a negative change in total energy. Does that make sense? So if this number here, if the number here is a negative number, that means that the reaction's getting hot. Another way of saying that is what? It's an exothermic reaction, right? It's a reaction that's getting hot. It's releasing heat. Exothermic reaction. Okay, so that's very simple. If this is a negative number, the reaction's getting hot. Okay, which means if that's a positive number, the reaction's getting cold. Okay, if you have a positive change in enthalpy, that means it's absorbing heat. Absorbing heat, which means feels what? Feels cold. And it's an endothermic reaction. That means what? Okay. All right. You got to listen to this. Okay, this is a little bit of a mind bender. If my drink here feels cold, I touch it, it feels cold. Do you know why it feels cold? Is it transferring cold into my hand? No. What you need to know is that cold is not an entity. Cold is not a thing. Cold is just the absence of heat. Does that make sense? So when I touch this drink, if it feels cold, do you know why it feels cold? Because it's sucking heat out of my hand quickly. And my brain interprets that sudden drop in heat from my hand as cold, right? Does that make sense? So heat moves. Cold doesn't move. Heat moves. And if heat's moving away from your body, if something's absorbing your heat, you feel cold. If something is releasing heat, then when you touch it, it transfers heat into your hand, it feels hot. Does that make sense? So a reaction with a positive delta H is a reaction that is absorbing heat, feels cold. It is an endothermic reaction. Okay? So again, if you have a negative number here, that's a reaction that's getting hot. If you have a positive number here, that's a reaction that is getting cold. Okay? And that's it. That's all you need to know about that. Okay, so what's T? What's T? T is temperature. Okay? So let's talk about that. T is temperature. Well, temperature. Okay, T is temperature. And not just temperature, it's temperature in the units Kelvin. Not degrees Kelvin, just Kelvin. Okay, temperature in Kelvin is a lot different than temperature in Fahrenheit or temperature in Celsius. Okay, temperature in Kelvin, the scale is positive. That's what you need to know. The scale is positive. What does that mean? Kelvin cannot be 0 and cannot be negative, nor negative. Okay? Kelvin, if you know anything about physics and the temperature in Kelvin, Kelvin can never reach 0 because that would be absolute 0, which you can't technically achieve. And Kelvin cannot be a negative number because that would be even lower than absolute 0, which that's just impossible. Okay, so all you need to know is that this number for T, it can't be 0 and it can't be negative. So what number can exist for t? What number can exist for t? What are the only sets of numbers that can exist for t? Only positive, right? So you could write here also must be positive, right? Positive. Must be a positive number. So usually what I like to do with t is just set it to 1. You see that? Just set it to 1 because 1 is a positive number that you can work with and it makes your math very easy, okay? A lot of times I set t to 1. Okay, so what else? Now what else is there? S. Delta S, actually. Change in S. Do you guys remember what S means? We talked about S before. Back here, do you guys remember? Look. Entropy or disorder. Remember what I said the units are? The units for entropy are big S. Okay, so entropy or disorder means big S. That means disorder. So the bear is releasing a lot of disorder, right? Okay. The solid has less disorder. Liquids have more disorder. Gases have the most disorder. So S is increasing. Okay, so what's S? S is disorder. S is entropy. S. So what can we say about that? A reaction with a positive change in S. Okay, a positive. Oh, let's start with a negative change in S. That's how we've been doing. A negative change in S. You know what that means? A negative delta S. That means that the disorder is. Are we having a reaction that's increasing disorder or decreasing disorder? Well, a negative change in S means that you started with a higher value for S, more disorder, and then you ended up with a lower value for S, less disorder. So disorder is decreasing, okay? And that means more order, right? Does that make sense? So if I were to mix two things and it becomes like a solid, I mix two liquids, and you know liquids are a lot of disorder, right? And those liquids become a solid. Well, that would be an example of a reaction where you're increasing order, you're decreasing disorder. Does that make sense? So try to follow that. Okay. But what if I had a reaction that increased disorder, right? Positive delta S. Positive delta S. Well, in that case, what's happening with disorder? You're going from a low disorder to a higher disorder, so disorder is increasing, which means less order. Okay, so that's that. That's that. Now you know every part of this equation. Delta G, negative delta G, spontaneous. Positive delta G, non-spontaneous. Delta H, negative delta H, exothermic, gives off heat, feels hot. Positive delta H, absorbs heat, gets cold. T, Kelvin. Kelvin can only be, like, let's say 1 or greater, like a positive number. It can only be a positive number. We'll deal with this more later, but just set it to 1 because 1 is a good round number that's positive, and it makes your math very easy, okay? And then we have delta S. Remember what delta S means? Change in disorder. If you have a negative delta S, it means disorder is decreasing. You have less disorder. If you have a positive delta S, that means disorder is increasing. You have more disorder. All right, so let me take a quick break, have a drink, so I can, get my dry mouth ready to talk some more. And let me come back. And when I come back, I'm gonna explain just how we can make use of this information. Like, how can we really understand what Gibbs was trying to tell us with his equation here, and what it relates, and how it relates to all of these factors that we just talked about: G, H, T, and S. Okay, so let's take a quick break. Break time. And we'll be right back with the information about that. Hey everyone, welcome back from break time. All right, so I had just left off talking about the Gibbs equation and how each part plays a role. We talked about delta G, we talked about delta H, we talked about T, delta S. And remember, I told you that t, we're just going to set it to 1 so that the equation becomes straightforward. And the reason will become apparent in a minute. So let's go ahead and start. So what did I say a spontaneous reaction has? A spontaneous reaction? A spontaneous reaction has a negative delta G, right? So a negative number here would be a reaction that is a spontaneous reaction. Does that make sense? Let me move these out of the way. Maybe I can move these over so they're kind of out of the way. Oh, let's also delete this for now. Okay. Okay. Look at that. So a reaction with a negative delta G is a spontaneous reaction, right? Okay, now think about this. Let's think about what Gibbs was trying to tell us. When will a reaction always be spontaneous? Let's think about that. When will a reaction always give you a negative delta G? Can you figure that out? Remember, I made the math easy because I set temperature in Kelvin to 1, so we can ignore the temperature because it can't be 0 and it can't be a negative number. So if the temperature is 1, okay, what kind of number, a positive number or a negative number here for delta H? Let's look at delta H. What kind of number, and by what kind of number I mean a positive number or a negative number, what kind of number can delta H be to help delta G be negative? What do you think, a negative number or a positive number for delta H? The answer is, let me make a box, a negative delta H. Let me copy the delta sign. Okay, a negative delta H. Can you see that? A negative delta H will help delta G be negative. Does that make sense? The more negative delta H is, the more likely delta G is to be negative. Do you follow me? What about delta? So 1 is something we can ignore. What about delta S? What about delta S? What can we do with delta S to make sure that delta G is negative? Would we want a positive number for delta S, or would we want a negative number for delta S? What do you think? Well, a negative number won't help because if you have a negative number here, you're subtracting by a negative, so it'd be like you're adding. Does that make sense? So you don't want delta S to be negative if you want delta G to be negative. You want delta S to be positive. Does that make sense? So delta S should be positive. I'm sorry. Okay, so look at this. Let me ask you a question, okay, and think about this, and maybe even pause this and try whatever you want. Plugging in numbers, for example. Can you have a negative number for delta H and a positive number for delta S? Can you have that and not have a negative delta G? Or will it always result in a negative delta G? Think about that for a second. So, and you could pause this and try whatever you want. And by try whatever you want, I mean, for example, you could say, okay, for delta H, I'm going to plug in some value. I don't know. I'll plug in minus 10, right? Does that make sense for delta H? I'll plug in minus 10 for delta H. And then for delta S, I'll plug in, I don't know, plus 100, right? 100. And you could do the math there and figure out what's delta G. Well, your delta G is going to be negative, okay? And then you could say, what if I had a negative 100 here and a plus 10 over here? Again, your delta G will be negative. So plug in whatever negative number you want here for delta H. plug in whatever positive number you want here for delta S, and you will see that based on basic arithmetic, right? Basic arithmetic, delta G will always be negative. So you know what that means? What can we say? This is what that means. Are you ready? Delta, whoops, sorry, I don't want that. Okay. Delta G will always be negative. Delta G will always be negative, and the reaction will always be spontaneous if that's right, delta H is negative and delta S is positive. Does that make sense, you guys? So you know what Gibbs would tell us? Gibbs would say if a reaction has a negative delta H and a positive delta S, it's by definition a spontaneous reaction. It's impossible for it not to be spontaneous. It's impossible for it to not be delta G minus delta G. Okay, what's another way of saying that? Another way of saying that is if a reaction gives off heat, because do you remember what minus delta H means? It means gives off heat, feels hot. If a reaction gives off heat, if a reaction feels hot, if a reaction is exothermic, and the reaction is positive delta S means disorder is increasing. With a positive delta S, reactions that give off heat and increase disorder are, by definition, spontaneous reactions, and they cannot be non-spontaneous. Does that make sense? Okay, but what if I was worried about having a non-spontaneous reaction, a positive delta G reaction? Then what would H be? A positive H would help you achieve that, right? Okay, and what about delta S? How would you end up with a positive number here? Well, a negative times a negative would be a positive, so a negative delta S would help you, right? Negative delta S, positive delta H. Just think about it. Again, do your trick. The trick I showed you. Put a negative number for S, and then put, I don't know, a positive number for H. Any positive number, it doesn't matter. You could put 10 here and minus 100 here. You could put 100 here, minus 10 there. Just solve it on your own, and you will see, no matter what you do, as long as you have a positive number for delta H and a negative number for delta S, no matter what numbers you pick in the world or the universe, delta G will always be positive, right? Does that make sense? So what can we say then? We can say that, what would Gibbs have said? Gibbs would have said that delta G will always be positive. That means non-spontaneous if delta H is positive and delta S is negative. And you're saying, why should I care about that? Well, think about it. It's actually very powerful stuff, isn't it? If you think about it, it's very powerful. What that says is if a reaction, if you mix this chemical and that chemical, for example, if a reaction's getting cold, remember it has a positive delta H. What does positive delta H means? Absorbing heat, feels cold. If a reaction's feeling cold, and the reaction is decreasing disorder, right? Minus delta S, decreasing disorder. Like the liquids are becoming a solid, for example. That would never happen for free, right? That's pretty interesting to know that something like that can't just spontaneously happen. Okay? If the reaction is giving off heat and increasing disorder, it will always happen spontaneously. If it is absorbing heat and decreasing disorder, it will never happen spontaneously. You see that? So that's pretty interesting to understand. And we understand that by this basic arithmetic as it applies to the Gibbs equation, right? So now here's some weird ones, right? What if my delta H, what if my change in total energy is positive and my delta S is positive? Then what? What if both of those values are positive? Well, then you're in a pickle, right? If delta H is positive and delta S is positive, does delta G have to be positive? Does delta G have to be positive? So let's think about it. So for example, if you have a positive number here and a positive number here, let's say you put 100 here for H and 10 here for delta S, right? So what's G equal? 100 minus 10, right? 100 minus 10 is plus 90, right? Does that make sense? That means your delta G is positive, right? But what if they were reversed? What if it was 10 here and 100 here? Then it would be 10 minus 100, which would give you the minus delta G, minus 90. Does that make sense? So did you see what happened there? Depending on what positive number you put here versus what positive number you put here, like how big those positive values are, you ended up with either a positive or a negative delta G, okay? So, and at this point, you might be wondering, this is why T is important. You see this T? This is why T is important. You want to know what T is, by the way? I should have explained this earlier. But T, or temperature, is just the ambient temperature in which you're doing the equation. If I'm mixing test tube 1 and test tube 2, and I'm mixing it at room temperature, which is around 24 degrees C, 273 Kelvin or whatever, it's the temperature of the room you're doing the experiment in. It has nothing to do with whether the experiment is giving off heat, getting hot, it's exothermic, or if it's absorbing heat, getting cold, that's endothermic. It doesn't have to do with that. It has to do with what is the environment temperature, what is the temperature of the surroundings, right, when you're doing the experiment. So have you ever noticed that sometimes experiments don't happen, they don't work until you turn up the heat a little bit, till you jack up the heat a little bit? Because and this is why. Look, when this value is big, you have more of a chance of having a negative delta G, right? If this value here on the right is small and this value is big, right, then you have a harder time having a negative delta G. So if you've ever wondered why you need to turn up the heat a little bit to get a reaction to go, that's because of this here. But anyway, you don't need to know all that. What you do need to know is this, okay? This is what I need you to know. Delta G may be positive or negative, right? Positive or negative, spontaneous or non-spontaneous, if delta H is positive and delta S is also positive. Does that make sense? And it depends on depending on the values, right? Does that make sense? Did you see when we had a big number here and a big positive number here for H and a smaller number here for S, then it was a positive delta G. When we had it reversed with a bigger number here and the smaller number here, then it was a negative delta G. You see what I'm saying? So if you have a reaction, for example, if you have a reaction that's getting cold, it feels cold, but it's increasing disorder, so positive delta H and positive delta S, then depending on the values of both, how positive is H, how positive is S, and also depending on the temperature, Kelvin, then yeah, it might be spontaneous, minus delta G, it might be non-spontaneous, positive delta G. Does that make sense? And the same thing applies if you have a negative delta H, see a negative delta H and a negative delta S, right? You see what I'm saying? Same thing applies. So let's do this way. Hold on. It's easier. Okay, if I have a negative 100 minus a minus 10, in this case I have a negative delta H and a negative delta S. What is my delta G? Is it positive or negative? Okay, it's going to be negative, right? Because a negative 100 plus 10 would be a positive 90, right? Does that make sense? You guys follow me? Okay, positive. But what if those values were reversed? You see? What if I had negative 10 plus 100? In that case, it would be a positive 90. I'm sorry. Yes, a positive 90. Okay, positive 90. Okay, I don't know if I said this correctly the first time, but if you have it this way around, it would have been a negative 90, right? Negative 90. If you had a more negative number for H and a less negative number for S, it would have been a negative 90. If you had it the other way around, right? The other way around, it would be positive 90. So again, what would Gibbs say? Delta G may be positive or negative if delta H is negative. And do you remember what delta H is negative means? It's giving off heat. And delta S is also negative. In this case, again, it depends on the values. Okay, did you guys follow that? So that's pretty powerful stuff if you think about it. Again, Gibbs set out to figure out whether a reaction is going to be spontaneous or non-spontaneous. He figured out that it depends on the parameters change in enthalpy, Kelvin, and change in entropy. And what did he find? He found that when reactions have a negative delta H and a positive delta S, they are always spontaneous, always negative delta G, right? Oh, let's do this. Okay. Again, if they are negative delta H and positive delta S, then it's always spontaneous. If it's the opposite, positive delta H and negative delta S, then it's never spontaneous. It's always non-spontaneous. And if it's either plus, if it's plus, it could be positive or negative depending on the values and depending on the temperature. And if it's negative, same thing. It could be positive or negative depending on the values and depending on the temperature. Okay, so I hope this makes sense. This is the most straightforward way of explaining it. By the way, everything I just explained is summarized on this slide here about Gibbs equation. This slide here explains everything that I just did on the previous slide. When is a reaction always spontaneous? When is it never spontaneous? And when can it go either way? So if you understand that, you understand a good deal about Gibbs free energy. And there's one last thing, or actually two last things I want to share with you before I finalize this particular part of Chapter 6, Part 2 of 3, and that is, real quick, I want you to know that instead of saying delta G, or I should say negative delta G. Another way of saying negative delta G means spontaneous, but it also means exergonic. Okay, so when someone says exergonic reaction, they mean a negative delta G reaction. They mean a spontaneous reaction. When someone says a positive delta G reaction, okay, a positive delta G reaction, that means non-spontaneous, and that means an endergonic reaction. So how does it work? Look at this. This is an exergonic reaction. Do you remember what an exergonic reaction means? It means negative delta G. Negative delta G. On the y-axis, you would have free energy. You know what free energy means again? You guys recall what that means? Free energy is G. Okay, free energy is G. Okay, so G is on the y-axis here, and they're just showing you in general what happens in a exergonic reaction. The free energy goes from high. Reactants means what you start the reaction with. The reactants have a high G value, a high free energy, and then the products end up with a lower free energy. So what's your change in G? You went from a high G to a low G. That's a negative delta G, a negative change in G. And do you remember what spontaneous reactions do, exergonic reactions do? They release energy. So the reactants went from a high free energy, a high G value, to a low free energy, low G value. This released energy. It had a negative delta G, okay? And that's why it released energy, okay? An endergonic reaction, on the other hand, you start with reactants that have a low G value. You end with products that have a high G value. And so your change is from low to high G value. That's a positive change in G, positive delta G. And look what happened. You required energy. Energy was required to allow this to happen. Okay? So just know that when you have a negative delta G, it's a spontaneous process. But when you have a delta G of 0, this can most easily occur in an isolated system. Delta G equals 0 means you're at equilibrium. That means no work is being done. Okay, so when we come back for part 3, I'll explain how we could apply this to a process called energy coupling in the cell, how we could make sense of how ATP is used in the cell, how the cell does work, okay, things that it wants to do like chemical work, transport work, mechanical work. We're going to talk about all that when we come back. But that's it for part 2 of 3 of chapter 6 of Thermodynamics and Metabolism lecture. Thank you for joining me, and I will see you guys next time.